Thank you. So I'm here today to talk to you about how changing small molecules can change the world. One of the most important lessons I want you to take away from my talk today is a message about chemical custodianship. So I wanted to start my talk today by telling you about what it is. All of you, probably even this morning, have thrown away a piece of rubbish. In doing so, you've used the rubbish for whatever you're going to use it for and thrown it away. These days, as a society, we're becoming ever more aware of the effects of chemicals in our rubbish. And you might even think about this sometimes, in fact I hope you all do, if you ever throw away a battery or a fluorescent light globe. If you throw them away, you know they've got some chemical in them and you've got to throw them away in a special way. And in doing so, you've taken chemical custodianship. You've thought about where you're throwing your waste away. I want to talk to you today about small molecules. Small molecules are a little bit harder to understand in that black and white, good, bad kind of way. Small molecules give us energy. They give us fertilisers. They are some of the most important molecules that make up our planet. And they may also provide a solution to some of the world's most important problems. Let me start and take a step back from the molecules and just let's have a conversation about what the real issues in the world are today. If I was to ask you, as an audience, what you thought the issues were, I think you'd come back to me with things like poverty, hunger, climate change, access to clean drinking water, global population. All of these things fundamentally come down to one thing, and that is that we have more and more people and a limited number of resources for those people. Everybody in the world wants the same thing. When there's inequality, there's conflict. People say these problems are related to population growth, and that's probably kind of true, and that's a really hard problem to look at really trying to solve. And I'm a chemist, and so I say, well, what can chemistry and physical sciences teach us about this problem, and how can we make some steps forward in terms of trying to solve it? The thing I think that all these conflicts come down to are two things, and really they're the same thing. They're energy and food. If we had enough of those things and they were close to free, the large majority of the problems in our world would go away. So what have those things got to do with small molecules? Well, small molecules are our energy molecules, our energy carriers. So if we can understand how to change them and how to control them, we can make energy and food free. But let me just start by introducing my friends, the small molecules. I have on the slide here today 5 of my personal favourite small molecules, and being that I'm a chemist, I'm allowed to have personal favourite small molecules. So up on the left, they have water. Now, water is a small molecule. It doesn't have a small impact, though. If you think about it, it surrounds the planet. 2/3 of our planet is water. Moving across, we have carbon dioxide. My friend here gets a lot of bad press, and in his bad press, we forget some of the really fantastic things that carbon dioxide does for us. Without carbon dioxide, we wouldn't have photosynthesis. Unfortunately, when we burn fossil fuels, we make carbon dioxide, and that has a negative effect on the world through global warming. And the final one on the right there is oxygen. You breathe that every day. Without it, you die. If you look across the top, you can see all those molecules have red spheres in them, and those red spheres are oxygen. Fundamentally, when we burn a fossil fuel, we take carbon and we join it together with oxygen, and it spits out and it makes carbon dioxide and water. Now, I could have told you the story of carbon dioxide today as a fundamentally important small molecule transformation, but I wanted to share with you a very similar process that I think has had in some ways a bigger impact to our world population than the story of carbon, and that's the story of nitrogen. And at the bottom of the slide there I have 2 molecules, and you can see they've both got blue associated with them. The one on the far right is nitrogen. We chemists call it dinitrogen because there's 2 nitrogens stuck together. And to its left is ammonia. Dinitrogen makes up 78% of the atmosphere, and ammonia is an important fertiliser. So all of these molecules are really fundamentally very important. So the thing about nitrogen is it's really important for energy, and you might not immediately see why. Now, most of our energy in the world comes from photosynthesis. Now, at some point as a chemist, I stopped thinking about the world like everybody else does and started thinking about it in terms of chemical reactions. What photosynthesis does is it fundamentally takes in carbon dioxide and water and spits out useful stuff like glucose. But the thing about that reaction is it's limited by nitrogen. And you might think, limited by nitrogen? You just told me that the atmosphere is made up of 78% nitrogen. How can photosynthesis be limited by nitrogen? But nitrogen's needed in small quantities for photosynthesis. And the problem with nitrogen is that plants can't see and use all sorts of nitrogen. In fact, the form of nitrogen that makes up most of our atmosphere, the plants can't use at all. So in order for plants to use it, it needs to undergo a transformation. We chemists call this process nitrogen fixation. So we've changed it from the form that's in the atmosphere to the form that plants can use. Now, this hasn't really bothered plants because plants over the years, for billions of years, have formed symbiotic relationships with bacteria that can do this transformation. But it bothered us a little bit. We discovered about 150 years ago that we could improve photosynthesis and crop yields by adding nitrogen to our crops. And 150 years ago, when the world's population was still about 1.5 billion, we'd started to use up all the bird poo in the world that we could access that had come via this reaction. So what were we going to do? Well, it's probably a good thing that around the time of the First World War, a very clever German chemist called Fritz Haber was able to actually figure out how to convert this unfixed form of nitrogen into the fixed form of nitrogen. About a decade later, Haber Bosch was able to come along and industrialise the process, and it became known as the Haber Bosch process for transforming nitrogen or for ammonia production. This is a very important industrial process in the world today. And just to drum into you how important it is, if we look at the world's global energy use, 4% of it goes into just this process. And if 4% isn't enough, if we talk about hydrogen, another small molecule, 50% of the world's hydrogen goes into this process. So we take hydrogen and nitrogen and put them together at high pressures and temperatures and make ammonia. Unfortunately today, most of our hydrogen still comes from fossil fuels, so this is far from being a sustainable process. But it's been a process with very big impact. I told you around 1870 or so, when the population was still less than 2 billion people, we were fighting wars over bird poo, and since then our population has grown. And why was it such a valuable commodity? Because it fed people. And if we look at the world population, and if I was standing before you in about 1950, 1960, the world was looking like it was going to have some very serious problems with starvation. So countries like India and China with rapidly growing populations were looking like they wouldn't be able to feed their populations as they grew. Combined with my friends, the chemical process, clever agricultural scientists were able to develop crops that could use the chemically fixed nitrogen. And if we're in year 2000, about 1 in every 3 people on the planet were supported by fixed nitrogen. And if I was to look at you today, it'll be 1 in 2 of us are supported by this industrial process that amends fertilisers to agriculture. So we chemists have done an absolutely fantastic thing, right? We've fed people. And that's a fantastic outcome. So with our crops, and we get 10 times more yield from our crops. This is great. But I told you my talk was going to be about chemical custodianship. So I want us to think a little bit about some of the balance. One of the problems with amending our crops with artificial fertilisers, and in fact with any fertiliser for that matter, is that we get runoff. Runoff means we now have fixed nitrogen where there was never fixed nitrogen before. So what we now have is nitrogen in the oceans. Now, I told you that this special form of nitrogen, which I have here, this special form of nitrogen makes photosynthesis better, which is great for our crops. But it has an unfortunate side effect, and that is that it makes photosynthesis better where there was no photosynthesis before. In the oceans, this means algae grows. And you might think, algae? Why would we care about algae? We have so much algae in the oceans these days that you can see it via satellite. Chemically, the problem with algae is that algae degrades over time. As algae grows, it consumes all the oxygen, and then as it breaks down, it dies. And this is creating large areas of the ocean that are becoming dead, literally dead. No fish, no plants, nothing can grow in them. We have ever large growing areas of ocean dead zones. So while we've fed people, which is fantastic, we've been really bad chemical custodians. So we have to really think about this balance and how we start to transform these molecules. It wasn't really my intention to bring you a gloom and doom story today. I wanted to talk to you about where I see some of the solutions to this problem. In my group at JCU, we do work on a special type of material called catalysts. And we specifically are interested in understanding catalysts that can mediate these reactions. And you might think, well, how would you even begin to understand those reactions? I mentioned to you before that at some point in my career as a chemist, I started walking along and just thinking about everything in terms of chemical reactions. So interestingly enough, I started my talk by telling you that bacteria have known how to transform nitrogen for 4 billion years. The fun thing about bacteria is bacteria are great chemical custodians. Bacteria can not only change nitrogen to ammonia, they know how to change it right back again. So if we could figure out what they were doing, we could be great chemical custodians too. It's similar to the story with carbon dioxide. If we just think about my friend, the tomato plant here, and the wondrous chemistry that the tomato plant is doing. Its leaves are green. The leaves are green and they're harvesting energy from the sun, and they're harvesting energy and using that to split water in two. Take a small molecule and split it in two. That energy is so much that we can take it and reduce carbon dioxide back to useful stuff like glucose. And you might think, well, that's wonderful, Rosalie, we know plants do that. How are we going to do it ourselves? You'd be surprised at how much we chemists know about how plants actually work. These days, we've been able to crystallise out proteins, and we can study their active sites and know at a molecular level how the structure works. So at the moment, lots of people around the world, including my group, are trying to figure out those reactions on a practical level, in an industrial way, so that we can actually use them. So if we could transform these molecules, we could save the world. Now, because I'm a chemist, I love chemical demonstrations. And I wanted to show to you today how a catalyst works. And really, it's really important to see how a catalyst works, because you can begin to understand how we can start to address this problem. Now, I really wish I could have shown you a catalyst that would do these reactions up here. In fact, I think all of us wish we could do these reactions really fast and explosively so that we could demonstrate them, because we would solve a lot of the world's problems. So I'm going to show you a different chemical reaction. I'm going to show you how I can break hydrogen peroxide apart. Now, hydrogen peroxide is a molecule a little bit like water. It is a small molecule, and you'd be familiar with it too if ever you had dyed your hair blonde. Whenever someone has blonde hair, they've inevitably used hydrogen peroxide to make it go blonde. If you're familiar with hydrogen peroxide, you'd know that over time it slowly degrades. We can really speed up that reaction by the introduction of a catalyst. And I have here today a manganese catalyst, and it's just a little manganese oxide, which you can see it's a little black powder in the bottom of the jar here. Interestingly enough, that catalyst is very, very similar to the material at the centre of photosynthesis that splits water. Hydrogen peroxide and water are sort of close to related to one another. So there are some correlations there to understanding this reaction. So what hydrogen peroxide is going to do with this reaction, it's going to change into oxygen and water. So I don't know if you can see it bubbling away there, but what you can furiously see is bubbles forming. Those bubbles are just oxygen and water. I couldn't have really brought anything that was going to be much more than that into here, but what hydrogen peroxide is doing is it's breaking down into oxygen and water. I had an important final message for you today, and that was that small molecules have changed the world, but our custodianship of them would change our future. And this is true about whether we're talking about carbon dioxide or nitrogen. And I don't know about you guys, but if we change something for our benefit, we have an obligation to figure out how to change it back. Thanks very much.